Keep the sound is fine, right? Oh. Yeah. So let's continue. Let's recall what we had last time. So yeah, we discussed the models with n equals 1 and n equals 2 for symmetry, right? So so we discussed some model which was so n equals 1 secretly n equals 2 models. Model with Lagrangian that was given in superspace by the following expression. Psi. This was related to W prime, superpotential. We discussed quantization of this model that we tries to the superchargers that we studied in the first lectures. Although it's written in n equals 1 superspace, this model has secretly n equals 2, as we discussed, and that's because we've introduced two superfields, phi and psi, right? So in principle, one can at the end of last lecture, we also considered the theory that's just given by this simple action with 1 phi. So in this case, the Lagrangian is just L phi is something like x dot squared plus I dot. And this has only one supersymmetry, whose corresponding supercharge is proportional to px times chi. So this is n equals 1 supercharge. Dx is the momentum corresponding to x. So in principle, we could also consider generalizations of these models. So this is the kind of rudimentary sigma model, supersymmetric. This is a supersymmetric sigma model, and n equals 1 sigma model. With target R, the real line, parameterized by X. And chi is its kind of super partner, supersymmetric completion. So today we will study this kind of models, their generalizations. The n equals 2 completion will not bother us. So here it was imposed on us by the desire to have the potential term. So if you want to have a mechanics with the potential, somehow you are led to n equals 2. But if you don't want to have potential, you just want to have a kinetic term, sigma model like kinetic term, then you can just drop those terms. And so for today, we will not care about this. Yeah, so effectively we just set psi to 0. Okay, so what are the models that we're going to consider? So we will have possibly a set of superfields. So we generalize phi to a single superfield to a set of superfields, phi and 1, phi by n. They're all Grassmann even. bosonic. And we write down the following Lagrangian. So we will think of these phi's as coordinates of some manifold. Yes, so these are some coordinates. Some manifold that we call M. And we can write down the following Lagrangians that we call, let's call it L0. Yeah, which is just integral d theta I some gij all phi's d phi I ij dot. So this is a generalization of that term there, where we put some factors here. So this gij will play the role of metric on M. And so the purely bosonic part of this is yeah. So if you want to find the purely bosonic part, we just set the fermionic fields inside phi's to 0, right? I recall that that phi I we will henceforth denote its leading component by x, xi, j is I theta chi I. So if you want the purely bosonic part of this Lagrangian, we just set chi I to 0. In this case, there will be x here, and here is a so here we have theta d over dt, and here, so d over dt acts on the bosonic fields, and theta is integrated out because of the theta integration. So the purely bosonic part, so L0 is gij by dot gj dot. That's fermionic terms. This is the standard sigma model action plus fermionic completion that's needed for supersymmetry. Of the more general Lagrangian that we can write. So notice that the superspace Lagrangian should be Grassmann odd, right? Because we're integrating over theta, everything should be Grassmann even. So we can add odd powers of the superderivatives. You see here it's first power of superderivative, which makes it odd. We can add odd powers, right? So, for example, more general Lagrangian is as follows. So we write, first we have the same term. Okay, plus possibly higher terms, so higher terms, higher terms in D to the power, some odd power, which means that you can have odd degree forms, coupling to various odd degree forms. So this guy. You can also have some mixed terms with usual derivative entering and so on. Of course, so there are more general possibilities. So in principle, these higher order terms do not spoil anything. So they enter the Lagrangian either with one bosonic derivative or with no derivatives. So their contribution to the Lagrangian will be something like dc k plus 1 times, so with indices I1, etc., I2k plus 1, coupled to the fermions. So it will be chi I1, I2k plus 1. For example, there will be terms like this in the Lagrangian, also terms with one bosonic derivative. So there can be more than one bosonic derivative because each derivative comes with a factor of theta. So, in principle, those terms don't predict anything. It could be included, but today we will not encounter them, so we'll restrict ourselves to this Lagrangian with the form degree 3. There's one. But so today we will mostly speak about this first Lagrangian with this first terms. And so there are some comments actually made regarding this Lagrangian. So the first thing to notice is that this formally this form standing here does not have to be symmetric, right? So because it doesn't couple to any symmetric combination. It's a bilinear form. But one can show that its symmetric part can be absorbed in this C, in the 3-form C. So so without loss of generality, so I can assume J symmetric. Cool. Why is that? Because if you have a skew symmetric part, so suppose which we call B is skew symmetric, so suppose we have a skew symmetric part. Then you use that. This can be written as I jk j from k. So this is I jk d phi j d squared by k. Yeah, and this can be written as minus 1/2 bjk d of d phi j d phi k. So you just use the Leibniz rule and use the antisymmetry of B. So this guy is antisymmetric. And then you can integrate by parts. So this is 1/2 d. Okay, I also some I somewhere. I over 2 d L. So this means this is a exterior derivative of the form B, right? And it can be absorbed into C. So C is just shifted by C goes to C plus dB. So therefore, that's one reason we've introduced this cubic term that now we can restrict to GB symmetric. Now we'll write out this section in component to see what kind of model that gives. So the function of this will be that I will write it out now, but the point is that the G will be the metric, of course, of the sigma model. Then A will be a gauge field. Abelian gauge field on M, and C will be the torsion of connection of in tangent bundle of M. So first of all, we write out the metric term Gij. Make one calculation as an indication, then the rest I'll just write out the answer. So this will be Gij of x plus Gij times sin theta by k times I times I theta x theta. Sorry, I was trying to avoid confusion with the i's, but inevitably it kicks in. So I hope it's clear that there is an imaginary unit, which is I, and the index, they're not the same. Sorry about that. So that's the xj dot. Xj dot. And you need to pick a theta component of all this stuff. And so after some reshuffling and so on, this gives minus I Gij xi dot j dot plus chi j of j dot plus chi p or chi l gamma lkj xj. Oh, sorry, chi. This is j xk dot. So this is the purely metric part of the Lagrangian, and recall that it's all multiplied by I. Remove the I here, put the I. One combination. So what stands here is certain covariant derivative. Right, this is chi j, and then covariant derivative of chi j along the vector d over dt. D over dt. We'll discuss it a little later. So first, let's write out the remaining terms. The meaning of this is that it is the pullback of the Levi-Civita connection on the tangent bundle of M to the world line. Right, so we have our world line is embedded into M, and then here we have a tangent bundle. We can pull it back to the world line. Is X. This is X star. Yeah. Fermions, the skies, are sections of the tangent bundle, or more exactly of its pullback. So okay. The pullback of under X. Yes, X are our bosonic coordinates, right? They define the map from the world, this time to the target space. So fermions and supersymmetric theories, they could be thought of as vectors in the target space, restricted to the world line. And so they're naturally coupled to the pullback of the Levi-Civita connection. So pullback of the Levi-Civita connection is what is written here. Okay, so let us now write out the remaining terms. So then we have the gauge field term. I. This is AI X xi dot. This is the usual magnetic field minus I over 2 j I j. So F is dA, the curvature of this Boolean connection. This is the magnetic field. And we also have the reform term. Which has the following. Theta part. So this has the Form. This is 3I. X times xi dot j chi k plus 1/4 dc ljk lijk times chi l I j chi k. So if you have higher powers of D coupled to higher forms, you always get higher powers of the fermion terms coupled to the derivative of the forms. So altogether, the Lagrangian is as follows. So is J. We have the sigma model piece plus H field plus ij dot tilde dur dt pi j minus I over 2 of the answer. And so first you can see that there are these couplings to forms that are pretty uniform. These are derivatives of the corresponding forms. This is one form, this is the free form. So coupling to forms. And then the connection that entered here is so this is like this. So this is j dot and plus gamma jkm plus c jkm x k dot m. So you see one has a generalized connection. We will call lambda, which can be split into the Christoffel part, symmetric Christoffel part, and the symmetric C part. So C with upper indexes, we just trace one index using the metric. So this is a general connection that is a general metric connection. So here we have connection lambda. It's first of all it's metric. So this is in EM. It's metric. That means that it's preserved by metric. And second, it's possibly with torsion. Just a reminder, torsion is a takes two vector fields as an input. The definition is nabla x y minus nabla y x. It's contained with y. It takes two vector fields as an input and produces a third vector field, so it has three inputs. Also, supersymmetry somehow. So this is automatically antisymmetric in the lower two indices, but supersymmetry somehow requires that it's totally antisymmetric, right? So there's this C is a three form, so this is totally antisymmetric. So that's like consequence of supersymmetry. Okay, so this is the rather general one-dimensional sigma supersymmetric sigma model with n equals one supersymmetry. Like I say, you can add higher forms and so on. That just complicates a bit more the situation. And the question I would like to ask now is what's the supercharge of this model? What really supersymmetry means here? So supercharge. So first, I remind you that in superspace, we know. I mean, we want the quantum supercharge. We want an expression for the supercharge as a function, right? We want as a function. On phase space. So phase space here is the supersymmetric version of cotangent bundle of them.
Cotangent bundle where five of
no, I think it's so it's a bit so I think it's T star of Tm with reverse polarity. So, or maybe it's not correct. So maybe it's maybe I think it's okay. Let me. I think that the more proper way is probably to write it as T star plus phi T of M. I think this is probably correct, right? I mean, we have a bosonic, still bosonic coordinate living in T star, plus we have a fermionic guy living in the tangent. Yeah, it's correct. Yeah, I think that's right. So basically here we'll have P, coordinate P, momenta, and here we'll have the chi's. And on M we have the X. So so we want this as a function on phase space. Then eventually we want to quantize it, so it becomes an operator in Hilbert space. But the easy thing is that we know what the supercharge looks like in superspace, right? Because it still looks the same as before. So this is just minus I as a differential operator, d theta plus theta d over dt. Acting on our fields, u pi j. So just gives ij plus theta j dot. So the variation of x is epsilon chi j, and variation of chi j is I epsilon xj dot. So now the point is that we want to express these variations in phase space. We actually want to write our model in phase space and Hamiltonian formulation. And then we want to find a function q whose Poisson brackets with these guys will give this variation. So we require that this is epsilon u with xj. So I don't know, maybe this should be so this is a supercharged in superspace. And we're looking for q as a function on phase space. So this is I epsilon, this epsilon anticommutator q with chi j. But first we need the expressions in the phase space. So to this end we introduce the momenta p pi, definition the derivative of Lagrangian by xm dot. They have the look follows this is a 2 plus lambda j k plus ai. So this is the momentum. So from this we express the velocity. So we find that the delta chi j is I epsilon epsilon over 2 g jk ek minus ak minus I lambda lambda k l ij I l. So this is the the variation of chi, and the variation of x is epsilon chi. And we don't really need to introduce any momentum for chi because let's recall how the reflexive form looks like, right? So basically, so the prototypical symplectic form. Let's first recall the maybe the prototypical symplectic form looks like. Okay, so I'll just start with some elementary supersymplectic form. So our Lagrangian, some elementary version of the Lagrangian is p x dot plus I chi dot. So that means that the elementary. So elementary symplectic form, the derivative of this. So this is dp dx plus I dk dk. Then we recall that what is the Poisson bracket? So Poisson bracket of f and g is by definition the derivative of function g along the vector field corresponding to f, where the vector field corresponding to f is the Hamiltonian vector field of function f. So there, I df omega equals d df. So just some definition, usual definition of Poisson bracket. So for example, if we want to find the vector field, so for example, we want to find a Poisson bracket of x and p. So this is a vector field corresponding to f differentiating p. So we need to find. So we write dx equals I Vx omega, and that means that I Vx is d over dp. And then substituting this here, we get that this is 1, right? So now we do the same for the fermionic. For the fermionic guy, we want to find a Poisson bracket of chi with chi. So we need to find a vector field corresponding to chi. So we write d chi is I v chi contracted with a symplectic form. And so it follows that I v chi minus I over 2 d over d chi. So I mean that I want to say that somehow chi is combines in itself both coordinate and momentum, right? So that's why we don't need to introduce any additional momentum. I mean the symplectic form looks like that. This is I over 2. 2 comes from the fact that you contract twice for the first and the second factor. So if we now, so that means that the Poisson bracket of chi with chi is you act with this vector field of chi. And this is minus I over 2. This is the upshot of this small calculation. What we need to do now is, so the slight problem with this, slight technical difficulty with this calculation that we want to do. So now we want to commute to calculate these Poisson brackets. So we need to know what are the Poisson brackets of the elementary fields. And the slight technical calculation is that our symplectic form is not exactly the elementary one, but rather has the following. So our real symplectic form that we have is d theta, where theta is sum over pi dxi plus I sum of gij of x by I dkij. So it's not really in Darboux form, the symplectic form. So chi is ppx, so that means that px in chi not the Darboux coordinates. Omega. Take a minute break and then we set some decision. So maybe before I discuss some technical complications in this case. So the technical complication comes from the fact that G is not a constant, not a constant. But first, let's discuss the case when it's a constant, so when we're dealing with flat space. Yes, so then we already actually written out this model in flat space, and flat space is just the Lagrangian is just sum over xi dot squared plus I sum over I dot. So and here the supercharge, we already know the supercharge. So as I discussed as we discussed at the beginning, this is just the sum over the momenta times I, or is proportional with. So here the and the corresponding Poisson algebra is simple, right? And upon quantization, what does it give? It tells you that commutator of xi and j, maybe k and pj is I delta kj. So this is quantization. And the anti-commutator of chi I k with kj is delta kj. So usually in coordinate representation, we say that the momentum is minus I d over dxj. So in this case, this operator Q supercharge is minus I ij d over dxj. And now notice that gammas satisfy Clifford algebra. Sorry, I mean chi's satisfy Clifford algebra. So this is so that means that chi's are just can be thought of as just being the gamma matrices. Right. So this is minus I gamma j dj. This is the Dirac operator. In R Rn. So that's the goal of our discussion. Will be the goal of our discussion to derive this also in the curved case. So basically, the claim is that the supercharge of the n equals 1 model is the Dirac operator. So, back to this slightly complicated one. Then we can derive the corresponding symplectic form, which is omega is pi dx I is pi j dki I dki j plus I dk I dx k dki j. So there is this extra piece. And so we want to compute yeah, so we want to you see we roughly expect that our supercharge will again be something like p times chi. So we need to know the Poisson brackets of chi with chi and p with chi. We want to know what is the chi with chi, p with chi. P with X will not be modified. So to this end, we compute the I yeah, so basically we want to know what is the vector field corresponding to P. So this is dpk is I vk omega. By definition, we want to know what is vk. And to find it, we first contract minus dpk plus I vk gij I ij, and we also compute E over d chi k omega. This is 2I gkj dkj plus I ti gjk ij dxi. So these terms. So this term, last term will not really play a role. So it's easy to see that dxi is I d over dp pi omega. So it will contribute to this vector field vk, but it will only matter when we compute the Poisson bracket of P with P, which we will not need. So kind of effectively, we don't care about this term for now. We will not need the Poisson bracket of P with P, and then we can just taking a linear combination of these two guys in such a way as to kill these two terms. We find that vk is minus d over dxk plus 1/2 dk gij and gjp chi I d over dxp. So this is the answer. So plus, like I say, plus d over dp terms, which we don't care about for the moment. Yeah, so it follows that P with x, vk with x, I delta ik, just by differentiating. And more importantly, that pk with chi I is 1/2 gpj no, so it's 1/2 dk vpj times ji times chi ip. So this is just acting with this vector field on chi. That's it. So the complication is that the P and chi have a non-zero Poisson bracket. which we have derived. And this is because there is this non-double term. So then these are all the Poisson brackets that we need to know. And then we can look for the supercharge. We can make some ansatz for the supercharge, which will slave from a reasonable flat space. So ansatz for Q. That the minus ik, k minus alpha I, ckml, IL. This is for now, this is some parameter, will be fixed from the commutation relations. I mean, the reason for this ansatz is that we know basically what we're looking for, right? We want Q with so Q, yeah, we want Q with xj be chi j, Q chi j to be I xj dot, which was like I over 2, the pk minus what we had before. So we basically pick some Q that will produce this kind of right-hand side. So the first term, the first Poisson bracket is easy to check. So we just compute Q with X. The only thing X has non-trivial Poisson bracket with P here. It just produces chi there. It's easy. So the more complicated thing is this commutation relation. So this is precisely where you need to compute compute the brackets with chi with chi and P with chi, and also chi's enter here. So the ultimate result is that you collect various coefficients and so on and so forth. That Q with chi and j substitute from here is I over 2 djk k minus e minus I gamma mkl minus 3 alpha c mkl kl. And what should stand here is this lambda connection. This is what was here. So this should be lambda mkl, which leads to alpha being minus 1/3. So this fixes the coefficient. Means that there should be 1/3 here. And this is our supercharge. Use the correct Poisson brackets of all the variables. Notice that in a funny way, only the C the torsion enters this central supercharge, whereas the Christoffel symbols that should appear here, they enter the Poisson bracket, and this is effectively the Christoffel symbol. So then they generate together the connection. So this is the answer for the supercharge. And now we want to ask what it gives upon quantization. So more exactly, we expect to arrive at the Dirac operator. So we want to check that. condition. So for computation, it's actually much better to choose Darboux coordinates. So this was just kind of an illustration how one can do calculations in this framework. But it's better to choose Darboux coordinates. So to bring the symplectic form to a canonical form. How does one do that? Well, the point is that this term that's non-canonical can be eliminated by going to the field bind basis, right? So to the introduce field bind in the following way. So you say that Gij is a sum of Ej A, where A goes from 1 to n, the dimension of the manifold. So these EAs can be thought of as a set of orthonormal vectors at each point. More exactly, these are one forms, but they are dual to vector. Right. So this a set of orthonormal one forms. So what is called frame. And they're orthonormal with respect to the metric G, and this is just a completeness relation. And orthonormal with respect to G. And the reason why it improves something is that because we can now write the kinetic term of the fermions, which is I EKA, EAJ, okay, chi j dot has in canonical way, so I dot minus minus I A E G where I use the notation. I have changed variables, so now I have chi with Roman letters. So this is the chi with Roman letters. Is the contraction with the with this field bind. So I J by definition. So now we have a symplectic form with constant coefficients here, right? But at the expense of modifying the momentum. Why? Because, well, I mean, this derivative is actually dk EJA times x k dot, right? So, so effectively, the momentum, the p momentum corresponding to x is modified. So the momentum we call now p. With a new variable, so where chi a is fixed. So this is the old momentum, Pj minus I A chi B, DJ EKA, EB, EBK. So we modify slightly the momentum. And now what we want to do, we want to substitute this momentum in the supercharge. And I mean, in general, change variables to pass to this new highs and new momentum. So in these new variables, the supercharge will take the form, so minus KC K plus I A B. K minus I over 3 CABC. So close bracket here and just write this as minus so this is almost what we need. So the bracket of pi is now the flat one. So IA with IB is 1/2 delta AB. This is different algebra, maybe normalized in a small standard way, but still it's pretty fine. And P with X gives also the usual X A IB is I delta AB. And now the remaining ingredient is the spin connection that secretly enters here. This is the spin connection. So I will not give a detailed definition, but I will just recall some basic concepts. The point is that the tangent bundle to M, in which we usually were familiar with the Christoffel connection, and we're used to the Christoffel connection, is a vector bundle, and it can be viewed as a vector bundle associated to some principal bundle. So it will be maybe let's say that it's associated. Yes, this is as a metric. Associated via the standard representation to the SOM principal bundle. Which is called the frame bundle. So this is the frame bundle. So it's the fiber is the set of all frames at a given point. So frames means orthonormal frames at a given point. So those field binds E, AK are sections, local sections of that bundle. And it's So each frame can be viewed as an element of SON. So this is a principal SON bundle over on M. So then there is the general construction of associating the principal bundle, some associated bundles related to the representations of that the group. So basically, you take the same transition functions of the bundle, but you change the fiber of the group to the representation of the group. So the actual arrow kind of goes from here to here. So you have some frame bundle and some connection in this bundle. So you're given some connection in this bundle, which is called the spin connection. This is a spin connection. And this defines a connection in any associated bundle. So in this way, you can in principle derive you can get the Christoffel connection, for example. So in order to get the Christoffel connection, you have to make an additional assumption that this spin connection is torsion-free. And in general, but of course, torsion is not really ruled out in general relativity. So you could as well have connection with torsion. This will give you not the Christoffel connection, but some connection with torsion. So the spin connection is usually denoted by omega AB. It's antisymmetric, so it's minus omega BA because it belongs to the Lie algebra of corresponding group. So in this case, to SON. So if you require torsion-free, this means that the dEA plus omega AB by H EB equals 0. And such torsional connection is unique, so you can actually express it in terms of this ease, this equation. And if you then induce the corresponding connection on the tangent bundle, this will be the Christoffel connection. So there's an explicit relation, which I'll write out. So the explicit relation is as follows: that the omega AB is minus EJB okay. The relation between the spin connection and the Christoffel connection. So this is the torsion-free spin connection and Christoffel connection. So of course the gammas are also can be expressed in terms of E because the matrix is this term. So then there is another twist to this story that so the reason why this spin connection is useful is that we can now so we have a connection on the principal bundle, so we can use it to construct connections on other associated bundles, right? And of course, what we want is the spin bundle. So the point is that in certain cases, this SON principal bundle can be uplifted to the spin N bundle. So I'll call E tilde. So this is the principal spin N bundle. Spin N bundle or spin N spin bundle. So spin N is the covering group of SON. So the point is that the pi 1 SON is D2. And the for N greater than 2. So spin n is simply connected. Roughly speaking, what it means, when it might not be uplifted. So the obstruction comes from the following fact that when you construct a fiber bundle, I'll just say some general word. So you have some patches, and you have to have some gluing functions at the intercept of two patches, right? But then, so the gluing function is basically a g-valued function on the intercept. But then the intercept itself can be non-simply connected. So, for example, this guy is like v, b, so pi1 of v non-zero and empty. So you can take some path in v representing a non-trivial gamma. So it belongs to one of v equal to 0, and it's mapped. So it becomes some path. So the gluing function restricted to this path becomes a path in the group. So we have some image of gamma in the group. So we have some gamma tilde belongs to our group G. So in case SN, for example, and it's a closed path in SN. But SN is a quotient of spin n by d2. But it might not be closed in spin n. Right. So that's the potential of shaft. So that means that your gluing function is well defined as a function, is a map from your patch to SON, but not as a map from your patch to spin n. So that this is just a general idea of how this obstruction may arise. When I say that they're not simply connected and so on, the easiest, the easiest picture I have in mind is the overlap of two patches on a sphere, right? Equators. The overlap is not simply connected, and there you can have such non-trivial bundles. So the topological invariant that distinguishes the sticks is the so-called second Stiefel-Whitney class. So it's some U1s. So it's some, if it's EM, so the tangent bundle. So this belongs to the second homology of M coefficients in Z2. And its vanishing is the necessary and sufficient condition for the frame bundle to lift to the spin n bundle. So in this case, it's called, or minus called spin. I think mostly in our applications later on, we will only be interested in the case when M is a complex manifold. So here some simplification occurs. So if then this omega 2 is equal to the first term plus En modulo 2. So just a mod 2 reduction of the first term plus. For example, CPNs with n odd are spin. So the first one plus, first one plus of CPN is proportional to n plus 1 times some generator. So that means that CPN spin for n odd for example, the usual sphere. In this case, we can define the spin. We can consider the spin representation of spin m and construct the corresponding spin connection in that representation. And the sections of that spin bundle are the spinners on M, and the Dirac operator will be acting on sections of that spin bundle. So, what does it mean in practice? So in practice, it means that well, we have this algebra, Clifford algebra of chi's. So chi's will now be replaced by gamma matrices, right? So like I said, so chi with chi b, one of delta b. So chi a, something like 1 over 2 times gamma matrices. So here, so we'll replace this combination of these derivatives of the field binds with the spin connection from this formula. And it turns out that the symmetric combination, the Christoffel symbols will cancel out. And what will remain is only the spin connection. So the ultimate answer is that Q yeah, so it's yes, and we also replace, of course, by k minus I d over dxk. You get that Q proportional to gamma A minus I k plus I. Gamma A, gamma B, gamma C. So this can also be fully anti-symmetrized, right? Because C is fully unsymmetric, so it can be anti-symmetrized. There's some combinatorial factor. Polarized. So this is the standard way that the Dirac operator is coupled to the spin connection, right? So this is a so basically this commutator just arises from here. So you replace chi's with gamma matrices from this term. This is the derivative, then there's a gauge field. Well, that's how it comes. So, well, the upshot is that the supercharge of the n equals 1 sigma model is a Dirac operator, and in general, it can be coupled also to higher forms in a similar way. That's the and with one supercharger. And there's one Figma model. The operator. And generalized Dirac operator. And as we mentioned, that we generally require that's well, okay. This has to be a operator in some Hilbert space. So the Hilbert space will be a space of sections of the spin bundle over our manifold equipped with L2 norm and so forth. But we want it to be Z2 graded. We want the representation to be Z2 graded. So our Hilbert space should be Z2 graded, and Q should respect the grading. To be Z2. It must be. Graded. And at least in general, it doesn't have to be. I mean, for this construction to work, the construction that I've described, the grading hasn't been imposed yet. But one case where it certainly is Z2 graded is when the manifold is even dimensional. So n is to n. So this is dimension n. Because in this case we have the so-called gamma 5 matrix, right? So gamma 5. It's usually called gamma 5, but it's be called gamma 2n plus 1, which is the product of all gamma 1s tetra gamma 2n with some appropriate factor. The main property is gamma 2n plus 1 matrix. Two main properties. That first, its square is 1. And second, it anti-commutes with all other gammas. And as a result, it anti-commutes with Q. With the Dirac operator. So this is precisely what is needed for the Z2 grading, right? So basically, in this setup, this gamma 2n plus 1 is what we called before minus 1 to the f operator. So so the bosonic and fermionic states are states of positive and negative chirality. What is called for the eigenstates of the projectors, 1 plus minus gamma 2. I mean the kernels of the projectors, gamma p plus minus. So p plus minus psi plus 0, this plus minus. This defines the positive negative chirality. Relative spinors. Or in other words, that the Dirac representation splits into two. The Dirac representation, so this Dirac representation of spin 2n is a direct sum of w plus w minus splits into sum of two Weyl representations. And the Dirac operator, it maps sections of the bundle associated to W plus with the two sections of bundle associated to W minus and vice versa. So as a result, in this setup, we will get n equals 2 for symmetry. It will be so actually here we have secretly n equals 2 supersymmetry. Well, actually, here we have n equals 2. Simple. And the complex supercharge, the complex, is just by definition, as you remember from before. So it's the Dirac operator multiplied by 1 plus. So this is the projector of the Dirac operator, like p plus minus, basically, like p plus. You see dagger is q by p minus. And one can check that this is so defined. Each of these is nilpotent, and their anti-commutator gives the. I mean, their sum is the Dirac operator. Their anti-commutator is some square of Dirac, which is the moton kind of. So yeah, so that's it for today. So we discuss this sample optimization of the n equals 1 supersymmetric system that leads to the Dirac operator. And next time we'll discuss n equals 2 superspace and some n equals 2 systems that lead to the Raman-Dolbeau operators. Then we'll discuss some relationships between them. I mean, between the Dolbeau and Dirac operator. So that's it for now.